Okay, welcome. We just covered elimination chapter E1 and E2. I have 3 lectures on elimination reactions, which is lecture 22, 23, and 24. But to conclude the chapter, I will be solving a lot of problems that falls under the chapter for elimination reaction. So this videos, the series of videos, will be very important to summarize what we know about E1, E2, and the competition between the E1 and SN1 kind of reactions. So follow all these problems and try to also cover the lectures that were already given in the videos for lecture 22, 23, and 24. So our first question, which is a very simpler question, would be to draw all constitutional isomers after the dehydrohalogenation reaction. Dehydrohalogenation reaction means it is an elimination of a hydrogen and a halide. That's what the elimination reaction is. So to begin, always an elimination reaction with obviously you need a base. That's the removal of hydrogen and the alkyl halide. First, identify what is the alpha carbon is, where the halide is. So the strategy would be, this is the alpha carbon where the halide is, and the beta position or beta hydrogens are this hydrogen next to the alpha carbon. So there is an alpha and beta carbons. The alkene or the double bond would be formed along the alpha beta carbons. So mechanistically, the hydrogen would be abstracted by a base, and this bond will collapse and the bromine leaves. So the first question is very simple. So it would give you a terminal alkene only. That is because this is one of the hydrogens that could be used for the elimination reaction. So the product is this. Let me count the number of carbons. 1, 2, 3, 4, 5, 6, 7 carbon. 1, 2, 3, 4, 5, 6, 7 carbon. So this is the only product because it says all constitutional isomers. That means if you have more than one beta carbon, you could have a possibility of producing more alkenes. So this is only alkenes that would be formed. This is a monosubstituted. These are hydrogens, obviously, from this hydrogen carbon. So this is just one substitution of alkyl group. So this is a monosubstituted terminal alkene. Okay. Now let's continue to the second one. You have this is the alpha carbon, but here remember now you have 2 possibilities. This is one of the beta carbons containing these hydrogens, and this is also another beta carbon. So in this case, you'll be getting obviously mixtures of isomers, of alkenes. So more than one product is possible for this. So let's just start by eliminating this hydrogen and this the halide, which is a bromine, which is a living group. This could be chlorine as well. So when we do that, we will just produce, this is a 10 carbon, 1, 2, 3, 4, 5, 6, 7, 8, 9, a 10 carbon compound. So one of the products would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is one of the products that's possible. This is by eliminating one of these hydrogens from the beta carbon. Now there is a possibility of also another beta hydrogens or beta carbon, from which you can eliminate one of the hydrogens and eliminate the bromine. Therefore, now the alkene, instead of being at 2 position, you would have it at 3 positions. So that would be here. Right here is the double bond. So the two products are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So instead of right here, the double bond would be right there. So now you have two different compounds, two different alkenes. So this is a 2-decene, because it's 10 carbon, 1, 2 position. We call this 2-decene. And this is a 1, 2, 3, 3-decene product. So those are two different constitutional isomers and two different positions of the alkene. The double bond gives you out of this. Now the third question is similar, just to identify what is a beta hydrogen, a beta halide, or beta hydrogens. Obviously this is one of the beta hydrogens, and this is the alpha carbon. This is on a beta carbon as well. So another one would be, this is also a beta carbon. So you have a possibility of 2 isomers again. So now we'll get a product where we have CH3, right, CH double bond, because we are using one of these hydrogens to eliminate this chlorine. So we have CH. So this is CH2CH. Another one would be CH3 and CH3. This is on 1, 2, 3 position, a 2 position alkene. This is at 2 positions, a double bond. The other one would be, here also would be at 2 positions, but at this substitution. So if you just use this hydrogen and eliminate this chlorine, you'd get another product, which is CH3, CH2, CH double bond, C, CH3, and CH3. Look how they are different. These are two different compounds. So here you have a 1, 2 position, but the metal is at 3 position. So this is a 2 metal, right? And the total carbon is 1, 2, 3, 4, 5 pent. And the alkene is at 2 position, 2-ene. So 2 metal pent 2-ene. And here you have a 2 metal. This is 3 metal. But here in this case, it's the alkene is at 2 position, but the metal is also at 2 position. So this is 2 metal, pent 2-ene, pentene. So this is a 2 metal pent 2-ene position. Both the metal group and also the double bond are at 2 position, but here the position is at 3 position is a metal, because the priority is for the alkene functional group. When we count from here, the double bond is at 2 position. So the 2 here refers to the ene, E-N-E, that's alkene, and here the alkene is at 2 position. The only difference is now the metal is at 2 and here at 3 position. Always when you are naming, the alkyl doesn't come as a priority. Rather, the lowest number for the alkene is the way you would count. So here, because you have different beta hydrogens and different alpha position, you'd get isomers of compounds. So this is just initial dehydrohalogenation reaction. So this is simple elimination reaction, but the main point here is if you have more than one position beta carbon which contains more than one hydrogen in those beta carbons, you would have different constitutional isomers for the alkene of the elimination reaction. Obviously here all of them have a base. That's how the reaction goes. It's just a generic name. I will just call it base here, because the main question is just to give the dehydrohalogenation reaction from the reactions. So we'll solve more problems. This is just an introduction to an elimination. Okay, let's continue more on the problems of elimination reaction. Here the question is a little different. The question is asking you, these are the alkene products that are already formed after dehydrohalogenation. So what kind of alkyl halide you would be using, and with a base you would get this product. So this is a reverse actually. So this is a product, these are the products of an elimination reaction, and the question is asking you to suggest what kind of alkyl halide you would start with so that you would get this product. So these are products. So the way we approach this would be, here you are getting a primary alkene, a terminal alkene. So what I would suggest would be, if I start with an alkyl halide where the chlorine or bromine is on this carbon, and the beta hydrogens or the beta carbon is this, I can get this product. That means what I'm suggesting is, if I have CH3, CH2Cl, or it could be a bromine or a chlorine, let me just use a bromine, on this carbon, and if I have CH2 on the beta carbon, this is beta carbon, and this is the alpha carbon. So if I have a bromine, CH2, 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 CH3, and if I use a base for dehydrohalogenation, I would just eliminate one of the hydrogens from here, and this bromine would leave. I would get this product. So that means if you start with this, you could get this product. So that's a reverse kind of thinking. What you start with, if you start with this alkyl halide, a primary alkyl halide, this is a primary alkyl halide, you get a terminal alkene of this sort. So 1, 2, 3, 4, 5 carbon, 1, 2, 3, 4, 5 carbon. So this is how you approach it. How about this? This is almost also the same. What we are going to do would be, if I have a bromine or a chlorine on this carbon, and if I have one of a beta hydrogen here, and if I use a base, I can dehydrohalogenate and get this compound. So the product is this. So the arrow would be this, but I would start with my proposal would be C2CH, and here CH2, instead of that is one of the hydrogens that would be eliminated, and I would just use CH2Cl, for example, chloride. So if you just have one of this hydrogen and a chloride on this alpha carbon, you could get this. So that is the starting material. So these are the starting materials to get this product. So the way you think is now it's a reverse. In organic chemistry, we call this retrosynthesis, meaning that you would be given a product and you would be suggesting the starting material you would get out of that reaction. So if you just put a base on that, you'd get that product. How about here? Here the double bond is an internal double bond. So something has been eliminated from either this carbon or from this carbon. So basically you would just suggest, if you have this, the suggestion would be that you would have, let's say, if I put my hydrogen here and a chloride or a bromide here, I can eliminate and get the same product I need. So basically you have two hydrogens here and one bromine there, and the rest of the alkyl side chain. Now, if you just eliminate this hydrogen, this bond would break, make the double bond, and that leaves. So here, that would create this product. So by just retroanalyzing, you'd just suggest this alkyl halides by dehydrohalogenation, meaning that by elimination reaction, you'd get this product. This is just to think backwards. So this is the, in this case, we have, this is the alpha carbon, this is the beta carbon. In this case, this is the alpha carbon, this is the beta carbon. So you need alpha and beta carbon, whereas alpha contains the halide. Here I have a beta, an alpha carbon right here, and this is a beta carbon. So the elimination always happens alpha beta. So alpha beta carbon should contain, the alpha should contain the electronegative atom or the leaving group, and you could have on the beta carbon an acidic proton or a proton that can be abstracted. So now we are slowly getting into elimination reactions and their mechanism and so on, but this is just an introduction to an elimination reaction. For an elimination reaction, remember, you always need to have an alpha carbon that contains an electronegative atom or a good leaving group, and also on the beta carbon you need to have hydrogen. That hydrogen would be abstracted by a base. All of this obviously need a base. So we'll study more detail on the bases. So those are the starting materials. These are the product alkenes. So this is alkyl halides. These are the alkene products. So we'll continue more problems on elimination. So we have another pair of questions here, and the question is asking you which double bonds can have stereoisomerism. This is just the structural studies of the alkenes, the double bonds, and asking you in this compound and in this compound. By the way, these are two natural products. This is pharencene and this is geraniol. These are natural products. They exist naturally. So the question is asking you, you have here 1, 2, 3 double bonds. For example, in these 3 double bonds, which double bond can have a stereoisomer? Which, in this 2 double bonds, which double bond could have a different stereoisomer? So remember, in alkenes, cis and trans, the alkenes, when you have a cis and trans alkene, or an E in general, E or Z isomer of an alkene, are stereoisomers. So for stereoisomers, let me evaluate this one. So if you have here this means this is CH3 and this is CH3. So if you have two identical substituents on that alkene, there are no priority difference between these two, this alkene would not be shown as a stereoisomer. So this alkene, this particular double bond, cannot have a stereoisomer. Okay, let me come to this one. When it comes to this alkene right here, this alkene is substituted, okay, here, this substituent, meaning all of this, versus this CH3, these are two different ones. Okay, next to this, if I have, obviously there is hydrogen, don't forget always that, and this hydrogen and this whole group is different. So basically this and this are different, this and this are different. When you have two different ones on the two different carbons, that should involve stereoisomerism. That double bond can be named as cis or Z or E as a trans. So let me evaluate this double bond. So basically what I'm saying here is this double bond has stereoisomers, meaning that it could exist as a cis or trans, as E or Z. That's what I mean. So, so if I just evaluate this, this is a larger group than this one CH3 group. So this is larger group. So the larger group is down here. In this case, between this hydrogen and this alkyl chain, this is high priority. So the high priorities are opposite. So this is actually a trans alkene, but in general, trans alkenes are E. So this is an E isomer on this double bond. So this double bond is an E or a trans. When it comes to this alkene, because it has two same things on it, which are hydrogens, no stereoisomers. We don't call any stereoisomer. Here we have two CH3, the same ones. We don't have a stereoisomer. For this, the double bond, this double bond is an E isomer. So I will take it one more, and if somebody asks you, please draw the Z isomer or the cis isomer for this compound. So the way I will draw that, I will have this, which is the same, right? I will have that, I will have this, and this, and here is where I would have the isomer, where I will put hydrogen here, this is CH3, and the alkyl chain, this chain would be down. Something like that. This is now the one I drew now. This is a Z isomer. Z isomer, not E. So Z, or it's also can be called as cis. Why? Let's see here. So between this alkyl chain and CH3, the priority is down here. More priority, more larger group is down here. And between this hydrogen and this alkyl chain, it is down here. So both large groups are in the same phase. They are facing the same direction. So those are Z isomers. So I just drew a pharacene with Z isomer of pharacene of a Z isomer, pharacene with E isomer. So these two compounds are chemically they are different. They are stereoisomers. So these are two stereoisomers, an E isomer and Z isomer. The only stereoisomer that can exist is only for the middle alkene, not for these two alkenes. Let's come to the geranyl, another natural product, and let's see what kind of stereoisomerism or which alkene. There are only two alkenes, so which one would be an stereoisomer? So basically, immediately, this is CH3, the same thing we did in the previous one. This alkene cannot be represented as a stereoisomer. It doesn't have two possibilities because you have priority groups on the same carbon. How about this carbon right here? This carbon, this is CH3. So if you just compare this alkyl chain versus this CH3, the larger group is down here, this whole thing. And if you just look at this CHO group and one hydrogen, also now the highest priority group is on the other side, not down, but up. So this is an E isomer as well, E isomer. So that double bond can exist as E and Z isomer. So if I were to draw a Z isomer for this one, for geranyl, I would just do this. I would just put CH3 up there, and I will just put H up here and CHO down here. So if you just were to see if this is right, so the larger group is down here, down the double bond. If you just compare this hydrogen with this CHO, the CHO is down in that carbon. So both the larger groups are pointing down, or they're in the same direction. These are Z isomer. The Z isomer of geranyl is this compound, where the alkyl is where Z and E are possibilities. So this is in analyzing an E isomer versus Z isomer. First of all, you should identify that whether that double bond can have E or E isomer. What it would be if you have two identical groups in one of the carbons on the alkyl group, that would not have an E or Z isomer. Only double bonds that have two different groups on that carbon. So this is a different priority than this. This is a different priority than this. So that could exist as either E or Z isomer. I also drew the E isomer and Z isomer. Here is the E isomer, and here is the Z isomer. So be familiar with redrawing. If you just see an E isomer or right in its Z form, and if you see some Z isomer, practice with drawing the E isomer. So this is just to show you what stereoisomerism is in alkenes. Alkenes could have stereoisomers, either an E or Z, or traditionally we call it cis and trans. When the larger groups are in the same direction, they are cis, or the larger groups are in opposite, they are trans. So E, Z, or so the E and Z isomer is equivalent to trans. Z is the cis. So those are equivalent or the same. In IUPAC naming, you'll find EZ isomers. So that's why we just use interchangeably. You could use those. Okay, we'll continue with more questions on. Okay, here we determine there are pairs of compounds in each section, and the problem is to identify what their relationship is between these two, and between those pairs. Are they the same? Are they stereoisomers? Are they constitutional isomers? So all these are alkene or double bond containing compounds. So we're gonna examine each one of them. Obviously here these two compounds have the same molecular formula, meaning that it is a C7 compound. This is also a C7. If we count the number of hydrogens, this would be 3 hydrogens here, 4, 6, 8, 10, 12. So this is a C7H12 compound. Similarly, if you just look at here, you have 2 hydrogens here, 4, 6, 8, 10, 12. So these are a C7H12 unsaturated molecule. That means it has a double bond and a ring system. But the way they are constituted, meaning that the double bond here is internal double bond, it is within the ring. Here it is an exocyclic double bond. So these compounds are not related as stereoisomers, not the same. Therefore, they are just constitutional isomers. So the relationship between these two is they are constitutional isomers. They are not stereoisomers, but they are constitutional isomers. Constitutional isomers are isomers of the same molecular formula, but they are differently constituted or joined in the chemical bonding. Let's see this compound pair. This is a diene, meaning that it is 2 double bonds. We call them diene. So this is also a diene, meaning 2 double bonds. A general name, they are dienes, but it has the same molecular formula as you see 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. So it is a C6. You have 3 here, 4, 5, 6, 7, 10. C6H10 compound. This is also, I believe, the same, C6H10. And also, in terms of the way the bonds are made, you have a single bond, double bond, single bond, double bond, single bond, double bond. You have single bond, double bond here, double bond, single bond, alternating double bond, the same, constituted in the same way. The second thing we have to ask is, are they stereoisomers? So for that, we need to examine each double bond, whether they are a cis or trans in each double bond. First of all, would this qualify as a stereoalkene? Yes, because the high priority here is down, but here it's up. So hydrogen is here, hydrogen is up. So the first alkene here is an E isomer. In this one also, hydrogen is up here, hydrogen is down here, but metal is up there. So this is also an E. So it's an E isomer. This is a 2E and a 4E compound. 2E, 4E. Carbon number 2, E, number 3, carbon number 4. So if we write a nomenclature, it would be a 2E, 4E, 1, 2, 3, 4, 5, 6 hexadiene, 2E, 4E, hexadiene, because the alkenes are at 2 and 4 position. Okay, let's see what the relationship here is. Here also, hydrogen is here, the hydrogen is here, down here, on this double bond. Here also, the alkene is up here, the hydrogen is here. So it is also E at this position and E at this position. So these two molecules actually same. These are same molecule. If you just rotate this down, this is a rotatable bond. If you rotate it, you can just achieve this. If you rotate this upwards, you could have just this. So these two are same molecule. Let's check this out. You have a double bond, a double bond. So we just check whether they are E or Z isomers. So you have ethyl here opposite. So high priority is up here, high priority is down here. So this is an E isomer. Ethyl is up here. On this one, ethyl is up here on the same side. So this is Z. So this and this are stereoisomers. Stereoisomers. They are an E and Z same molecule. Formula is the same, but the only thing is their orientation in space is different. So these are constitutional, these are the same molecule, these are stereoisomers. Let's check this out. Everything how they are bonded are the same, meaning that you have CH3 here, CH3, you have CH3 here on this carbon, you have CH3 on that carbon. The only thing you have to check on this is whether this double bond is an E or a Z. Let's see first of all the high priority between this carbon on this side versus on this side. The high priority is on the lower side. So high priority is the lower portion of the alkene, because this carbon has CH2, but this carbon has CH3 on it. So it's down here is the priority. Between these two, the high priority is also in the down side. So this is a Z isomer, Z stereoisomer, in the same side. The two larger group are on the same side. Let's check here. Obviously, this is the lower portion as compared to the upper portion. This is high priority because this has extra CH3 on this. But if you check here, the high priority is opposite side, not here. So it is in the other side. So this is an E isomer. So these are related as stereoisomers. So these are stereoisomers. So we identified now the relationship between each one of those. These two are constitutional isomers. These are same molecule. These are E and Z isomers. Therefore, they are stereoisomers. These compounds are also related as stereoisomers because this is the Z isomer and this is the E isomer. This we can continue into the next problem. Okay, continuing to the next question, we are asked to draw all isomers of molecular formula C2H2BrCl. So as you see, this should be an alkene compound because it's unsaturated. It has only 2 hydrogens and 2 halogens. That is a C2H4 compound. So that means we're going to start by drawing an alkene of 2 carbon. So if you have carbon and another carbon as a double bond, now you put all of the substituents, starting by putting the 2 hydrogens here and chlorine here and bromine here. So this is one possibility. It is C2H2BrCl. So this is one possible compound. Second one, I could draw CC double bond, still double bond. I could put chlorine here, bromine down here, and one hydrogen here, and one hydrogen there. This is one possible compound. And also, what's another possibility? We know stereoisomers are possible when the substituents are in opposite direction or in the same. So let's test this one, and then we'll label. So if it is chlorine is here, hydrogen is here, hydrogen is here, no, let's say bromine is down here, and hydrogen here. So let's see what they are, how they are related. These three different isomers, how are they related? So this doesn't have Z or E, cis or trans, because two of the same molecules, two of the same atoms are in the same carbon, so there is no distinguishing in priority between these two. So except you have chlorine. So this is just one alkene, a constitutional isomer, meaning that it is just an alkene which is constituted this way. Let's see this one. If we just examine this, the priority between the chlorine and hydrogen, priority would be given for the heavier atom, which is chlorine, high atomic number, and between these two, bromine is high atomic number. Both high atomic number are on the same side, so this is a cis, or we call it Z isomer. Okay, so this is a cis, or we can call it a Z isomer. How about for this one? If you just see high priority is between hydrogen and bromine, if you compare that, bromine is here. If you compare hydrogen and chlorine, chlorine is here. The two high priority atoms are opposite side. One is down, the other is up. So this is a trans isomer, or in general it is an E isomer. So these are related as Z and E isomers. So they are stereoisomers. Stereoisomers. So if you are asked what is the relationship between this and this, they have the same molecular formula, but they are not constituted the same way. Here you have hydrogen, here you have hydrogen. So they are not the same. So the relationship of this compound between this compound and the other two, they are constitutional isomers. The relationship between this and the rest two is a constitutional isomerism. But these two are stereoisomers. So the possible all isomers of a molecular formula C2H2BrCl are drawn here. This is a Z isomer, this is an E isomer, this doesn't have E or Z, but if you are asked to identify the relationship between this and this one, constitutionally they are different. So they are called constitutional isomers, even though they have the same molecular formula. So anything which has the same molecular formula but differently constituted is a constitutional isomer. So this constitutional isomerism applies as it relates to this compound compared with these two. So they are constitutional isomers between this and that also. So these are the relationships. These are the three different isomers you can draw for a formula, which is C2H2BrCl. But remember now, this alkene can be written as cis and trans. Whenever you have a double bond, check whether you could write Z or E, meaning cis or trans. So we'll continue more with another question. Okay, let's continue with our problem solving session. This problem right here is mostly on stereochemistry. As you see, we have a molecule here. It's called prostaglandin. It's a hormone responsible for cell inflammation. It's inflammatory compound or hormone found in in biological systems, in living things. So the molecule is a little bit exotic, and you can see it has double bonds here. Mostly we focus on the double bonds. And we want to know, for example, it asks you how many stereogenic centers are there. When we say stereogenic center, it's not referring to a double bond. If you remember a chapter in stereochemistry, anything that has 4 different substitution would be considered chiral or a stereogenic center. So let's start with question A. How many stereogenic centers do you see here? A double bond, sp2, will not have any stereogenic center. So let's start counting stereogenic centers. Obviously, immediately I can see this is one stereogenic center where you have OH, and this carbon is substituted to 4 different items. Again, this is also another stereogenic center, a tetrahedral carbon, which has 4 different substituents on it. That means it could have an R or S configuration. This carbon right here is also a stereogenic center. And this carbon right here is a stereogenic center. Now we just finished all of the stereogenic centers that are in the cyclic system. But here also, when you come here, you could also identify this has 2 hydrogens on it, so that carbon will not be a stereogenic center. This carbon is sp2 hybridized carbon because it has a double bond. It cannot be. So here you have CH2, 3 CH2 repeating units, so no stereogenic center on this chain. If you look at this chain, this carbon is sp2, so there is no stereogenic center for this. But remember right here, this carbon is substituted to 4 different things. If I just redraw this, it will be like having H, OH, and this. So that carbon is a stereogenic center. So I just redrew it. It was CHOH. So that carbon is a stereogenic center. If you remember now, we have 1, 2, 3, 4, 5 stereogenic centers. So for the first A, we have 5 stereogenic centers. This is a review in stereochemistry. Okay. Now, the next question asks you how many double bonds that can exist as a cis or trans are existing there. Obviously, we have 2 double bonds, right? So are these 2 double bonds exist as E, Z, or cis or trans? Yes. This has a hydrogen on it, this has a hydrogen. So if the 2 hydrogens are on the same phase, that would create a cis compound. If one hydrogen is above the double bond and one is down the double bond, it would create a trans. So now we have a cis and trans for this part. So we have cis, trans possibilities. If you look at this one is also, this hydrogen can be down here and this hydrogen can be up there, or hydrogens the two hydrogen would be in the same side. So there is a possibility for cis and trans. So how many double bonds that can exist as a cis and trans? Totally 2 here, cis and trans, 2 double bonds, meaning that this exists as 2 cis and trans isomer. This exists as totally we have 4 double bonds, 4 different type double bonds. That means you could have cis, trans, that is possible. And also, you could also have this is as a cis and this as a trans, this trans and this cis. So we could have cis for the 2, trans, let's say this is double bond 1, the top one is this, the lower one is this, top, lower, trans. When the top is also cis but the lower one is trans, is another combination. Now the top being trans, the lower one being cis is another combination. So you could have cis, 1 compound, 2 compound, 3 compound, 4 compounds. That means a cis combination, a trans combination, a cis trans combination, a trans cis combination. So a total of 4 different double bonds. So now it is asking you, the answer is 4 here. Now it is asking you what is the maximum number of stereoisomers. Stereoisomers include now the stereogenic centers as well as the cis and trans. Just considering the stereogenic center, if you remember, just looking at the tetrahedral geometry, the maximum number of stereocenters with 5 stereocenters would be to the power of n, which is to the power of 5. There are 32 stereoisomers. Just considering the tetrahedral geometry, meaning that the sp3 carbons. This is from the sp3 tetrahedral carbons would have 32 stereoisomers. So now you could multiply 32 times 4 for this, right? With this combination as well, 32 stereocenters times 4 different kind of cis and trans stereogenic centers, it would be 128 different compounds, stereoisomers. This compound can exist as 128, maximum number of 128 stereoisomers. That is the maximum possible number of stereoisomers. This is just a revision on stereochemistry, but as well as it, we also find out that a cis and trans exist for those double bonds. So we'll continue to another question. Remember, this prostaglandin is, as I already told you, an inflammatory hormone that is found in cells. Okay, I have 3 different alkenes on the board. As you see, the task is to identify the stability of the alkenes. That means to rank them according to their increasing stability as a compound. So these are 3 different types of alkenes. So the first thing you have to understand would be, it's per se, it's also applying Zaitsev's rule. That means a more substituted alkene is a more stable one. That's the general Zaitsev rule that we can apply on this. First, let's characterize what kind of alkenes do we have here. If you see compound A, which is an alkene, It's a terminal alkene, meaning one alkene. That means the alkene is at the H and it's less substituted. 1, 2, 3, 4, 5. A pentene. This is a 1 pentene compound. So it's 1 pentene compound. So if you just look at here, this is a terminal, and if you just rewrite it again, the structure looks like this. CH, CH2, CH2, CH3. So this is a monosubstituted alkene also, because if you just look at here, everything is hydrogen here, and everything is hydrogen here. If I just rewrite again this one here, also it should look like hydrogen here and a double bond here. So this is a, everything is hydrogen, 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 only one alkyl substituent on it. So it's also monosubstituted. Monosubstituted alkene. Substituted alkene. It's a monosubstituted alkene, meaning it has only one alkyl R group on it. So basically this is H, 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 alkyl group R. The R is this propyl group on it. So this is a monosubstituted alkene. Usually monosubstituted alkenes are the least stable ones. They react very quick. The reaction is very fast because they are not very stable. Monosubstituted alkene. Here, if you just look at compound B, you have one alkyl, which is ethyl group here, one methyl group here. It is rather a disubstituted alkene. Disubstituted alkene. The same, if you see compound C, it is also disubstituted. So we have a monosubstituted alkene, a disubstituted alkene, a disubstituted alkene. From our analysis, the least substituted one, the monosubstituted, is the least stable. Least stable. Now we know the order for, at least for compound A, is the least stable. How about when it comes to disubstituted? How do you figure out which one would be more stable? So if I have the same disubstituted, the way I can only determine their stability is by just looking at which one has the larger groups on the same side. That means a cis alkene is a little bit stable, lower stability than a trans alkene. So if I compare between these two, there is a clash. The two larger groups are on the same side, on the top. So there is a clash here that is possible. So that makes it a little bit lower stability than compound B. Compound B is trans. The two larger groups are opposite side. Hence, there is no steric clash between the two. They are far apart. They are anti-periplanar. So that means they will be more stable. So the most stable being B, the next stable would be C, the least stable would be A. So stability-wise, stability increases. A is less than C, C is less than B. So this shows increasing order of stability. This is increasing order. So if you are asked to write increasing order of stability, that is the order. Increasing order, stability. A is less than C, C is less than B. That means B is the most stable trans alkene. So both are disubstituted. Here this is monosubstituted. So in general, now as a conclusion, Zaitsev rule tells us a more substituted alkene is a most stable one. But in addition to that, the stereochemistry or the stereoisomer, which is a cis, is less stable than a trans. So this is a trans alkene, more stable than a cis alkene. So this is how you would rank, in general, any alkene. This is how you'd come up with stability of the alkene. So that means the least stable is the most reactive. It could react with something and change into different products. So we'll continue more on alkenes.